Hey guys, here we are with our last section in Chapter 7, which has all been about quadrilaterals, which are four-sided figures. So we had some special ones that we were talking about, especially parallelograms in those first few sections, and then we talked about rectangles, rhombuses, and squares in the last one. And there's different properties for each of those, as we saw. And now we're going to look at trapezoids and kites in 7.5 and look at the properties for those. So it says what are some of the properties of the trapezoids and kites. First, let's go and look at a little cartoon. Start us off here. Just Foxtrot is the name of this one. If you're not familiar, it's about a family, and so this is a brother and sister. He's the older brother. She's the younger sister. She's doing some math. I can't do these math problems. Why am I so stupid? If 2x plus y equals 60 and x plus 2y equals 75, solve for x and y. How the heck am I to figure that out? If two shirts and a sweater cost $60 and a shirt and two sweaters cost $75, what does each of them cost? Which does each item cost? Well, the shirts are $15 and the sweaters are $30. Duh. You aren't stupid, Paige, just weird. Come back, you still haven't told me how to solve the problem. So obviously he did tell her how to solve the problem in the language that she understood, but she didn't quite make that connection. All right, so let's move on to what we're going to do here. Off to the races. We're going to first talk about the vocabulary in this section. So page 217, go to that page and you'll see the top basically 5 vocabularies up there. Starting off with trapezoid, and what I would do is I would draw this figure there on your paper off to the right side, because this is definitely going to be a better maybe thing to look at than just what the words are, because always pictures are always helpful. First of all, the trapezoid. What a trapezoid is that it is a quadrilateral with exactly one pair of parallel sides. So this is a trapezoid. Here's your parallel sides right here, and those parallel sides are called the bases. So that's another vocabulary word. So the bases are the parallel sides of a trapezoid. Base angles of a trapezoid. So base angles of a trapezoid are two consecutive angles whose common side is a base. So we're looking at these green ones down below here. Here's base angles at the bottom with this base, and there's base angles on the top with this base. So those are base angles. When we're talking about base angles, we're talking about the ones here on either the bottom or the ones up on the top. And then the other one's a leg. So let me read this, actually, the rest of this part. A trapezoid has two pairs of base angles. For example, in trapezoid, we see over here A and D are one pair, and B and C are the second pair. The non-parallel sides, here's what legs are. The non-parallel sides are the legs of the trapezoids. So that's these guys on the sides over here, so these are not parallel. So trapezoids, again, only have exactly one pair of parallel sides. The other sides are not parallel. And then our last one is isosceles trapezoid here, and you want to draw this picture for isosceles trapezoid. So it's a trapezoid. You can see the two parallel sides. These are not parallel, so it's definitely a trapezoid. But if it's isosceles, what that means is that the legs of the trapezoid are congruent. So these legs here are congruent. You can see the little congruent marks there showing that this is an isosceles trapezoid. All right, so let's move on to the next part, which is this problem here. I'll just watch this one. This is from the book. So show that this quadrilateral ORST is a trapezoid. Then you can decide whether it's isosceles. So we want to first show that it is. So we see these sides look like they're the parallel ones. We want to just show that those are parallel lines based on the slopes of them. So find the slope of each one. You could do rise over run. You could see this one is going up 1 and right 2. This one's going to go up 2 and right 4. So you want to do that. Compare their slopes. The slopes would both be 1/2 when you simplify. So you can subtract the x's on top and the y's on the bottom. That's what they're doing here. So the x's of each point minus the y's of each point on the bottom, simplifying both to 1/2. So they are the same slope, and that makes these parallel lines. So that right there shows you that it is a trapezoid. Then you want to look at basically these sides over here. You want to see if these sides are the same length. So then decide whether this is isosceles. So if it's isosceles, that's what we want to now figure out as well. So the slopes of this are not the same, and so they're showing actually that these are not parallel. We can obviously understand that these are not parallel. We can see that they're not. but they actually did the same thing with those ones as well and found the slopes to show that they are not the same. So they're just saying that because it has exactly one pair of parallel sides, it is a trapezoid. And then we want to figure out the lengths of the legs here and see if they're congruent. And so we're going to compare the lengths of these legs here, RO and ST, and just using the, you can actually just kind of see the length of this one. You can count this one as 3 definitely. This one you're going to have to use the distance formula to figure out if that's the same thing. It's not 3. So you can see 2 square root of 2, or the square root of 8 is not going to be 3. If that was a square root of 9, then it would have been. So because these are not the same, then we know it's not an isosceles trapezoid. And so that's what we're looking at. On our extra practice number 1, so page 219, the extra practice, that first one, it says show that the quadrilateral with vertices, and it gives you the 4 points there, is a trapezoid. That's the first thing to do. Decide whether the trapezoid is isosceles. This last part we're not going to do right now. That's actually going to come later. So we're going to see this problem come back again, and we'll do that last part about the mid-segment of the trapezoid, as we will learn that in a little bit. So the first thing is just to draw a coordinate plane. So let's put the coordinate plane down like this here. So I would go about 4 from the bottom and then draw your x-axis, and about 4 from the right side and draw your y-axis going down. And let's go and put these points on here. Q is 0, 3, R is 0, 6. So you're going to start plotting these points. Each box would be worth 1. And once you plot all 4 points and you can label them, you can label Q, R, S, T, and then connect the dots. It should look like that. So Q is here, and then you got R is 0, 6 up here. And on this side you have S at -6 and 0, and then T is here at -3 and 0. And then just connect the dots, and you got your trapezoid, or what appears to be a trapezoid. We're just going to decide whether that, we're going to show that it actually is a trapezoid by first showing that there is exactly one pair of parallel sides, which we know these two, RQ and ST, definitely are not parallel. We can tell that just by looking at it. So really just show that these two here are parallel by looking at their slopes. You can again just do rise over run, or you could subtract the numbers. So first one here, if I do the slope of SR, it's going to be 6 over 6, which I'm just doing rise over run on this one because I can see it very clearly. So I'm going to rise 6 and run 6. 6 over 6 would equal 1. And then for the TQ, that's going to be 3 over 3. So I'm going to rise 3 and run 3. It's also going to be 1. So because these have the same slope, and we know these ones do not here, so that means it definitely is a trapezoid. It has one pair of parallel sides. And then to decide whether the trapezoid is isosceles, we would need to figure out the length of the legs here, which is ST and the RQ. So this one, since they're very clearly marked here, we can just count them. We don't have to use the distance formula. We can actually just count. We can see this one is 3 units long. This one's also 3 units long. So because the length of ST is equal to 3 and the length of QR is also equal to 3, they are congruent. That would definitely tell us that this is an isosceles trapezoid. Now, speaking of isosceles trapezoids, they have properties assigned to the isosceles trapezoids. So now a regular trapezoid doesn't really have any particular properties other than just the definitions that we've already gone through, but isosceles trapezoid has also these properties here, or these theorems. So an isosceles trapezoid base angles theorem is basically saying if it's an isosceles trapezoid, the base angles are going to be congruent. So your base angles at the bottom are going to be congruent to each other. The ones at the top will also be congruent to each other. There's a converse of that, saying that if you do have base angles in a trapezoid congruent, then you know it's isosceles. So if you're not told that it's isosceles, but you're told that the base angles, or one pair of base angles, are congruent, then that would tell you that it's definitely an isosceles trapezoid. And this last one, isosceles trapezoid diagonals theorem, is just saying, okay, if we have an isosceles trapezoid, the diagonals are going to be congruent. So from A to C, it's going to be the same distance as from B to D. And a rectangle had the same property. The diagonals were congruent in rectangles as well. So this is the same similar one to the rectangle, where the diagonals in isosceles trapezoids are congruent. Okay, so here's a quick one from the book. It just says the stone above the arch in the diagram is an isosceles trapezoid. Find the measure of K and M and J. It gives us L is 85 here. And so because of isosceles, we know that these are going to be congruent up on top. So K is going to have to be also 85 because of base angles. Right there, K is the same as L. That's the first thing to see. And then the second thing to see is now we can look at these are consecutive interior angles because we have parallel lines. Basically, these are transversals. So these would be consecutive interior angles, which are supplementary. These are going to add up to 180. And so we know that basically if we just take 180 minus 85, that gives us 95 for these other angles down here. So J and M are both going to be 95. So that's all that would be. Okay, so now we're going to look at the kite. So you've seen a kite before, I'm sure, in this shape. Now kites, sometimes now take on all different sizes and shapes, but this is like the basic shape of a kite that we have. I mean, I have some at home for the kids that are this shape as well, but then there's other ones that I have that are other shapes and other sizes. If a quadrilateral is a kite, so if a four-sided figure is a kite, then exactly one pair of opposite angles are congruent. That's our theorem for the kite here. So a kite's a quadrilateral. It's in this shape here, and basically the shape would mean that these two are congruent on top. So you have two pairs of kind of congruent sides. So the ones up here are congruent, the ones down below here are congruent. That makes a kite, basically. But the property here is that these angles here are going to be congruent. The ones on the opposite sides here with A and C. B and D would not be congruent here, so this kind of angle between the two congruent sides will never be congruent to each other. But these ones will be congruent always to each other if it's a kite. So here's a little example here. Find the measure of D in this kite, and it's telling us these angles here, which the ones are not congruent, are shown to us, 115 on top, 73 on the bottom. We know D and F are going to be exactly the same, so if we find measure of D, it's also the same as measure of F. And that's the first thing they want to say, is that D and F are the same, so we can kind of substitute this in here. And we'll use this, the quadrilateral sum, which is 360 degrees for all the interior angles. That's something we learned also in this chapter. So we can say, well, the measure of D plus the measure of F plus these other two are going to all equal 360. And the measure of F is the same as D, so we can substitute that in. And now we have 2 times the measure of D. We'll add these together and then subtract from 360. So we're going to say 188 for that. Subtract it from 360. That gives us 86. Actually, it doesn't give us 86 there yet, but subtract from 360 and then divide by 2, and that would give us the 86 there. So they did the 2 steps kind of quickly and didn't show both steps. But that's basically how you're just finding that. So if you find the measure of D, that's the same as the measure of F. Okay, problem 2 and 3, it says find the measure of K and L. So we're going to use the isosceles trapezoid properties and that property for the kite on 3. So this one you can see that it is an isosceles trapezoid. That's the first thing to recognize. That means you know you have those properties you can use, which ones we want to use here are the base angles one, where the base angles are congruent here. So M and L will be congruent. We're trying to find the measure of L. And if we know measure of M is 23, then we know the measure of L has to also be the same thing. That's 23 as well. So we can just go straight to saying that's 23 degrees for the measure of L. Then to find the measure of K, because these are parallel, and this would be like a transversal right here, these would be consecutive interior angles. So we could do that with consecutive interior angles. We may want to write that down here. I forgot to write it down, but consecutive interior angles on this one. And you can do that with saying 23, which is the measure of angle L, plus this one is going to equal 180. So these two add up to 180. So 23 that we know, plus the one we don't know. If you want to just put X here for that one, that's fine. And then just subtract 23 from 180, and you found that the measure of angle K is 157 degrees. So we know that's a 157 here. Another way we could have done this without doing it with the consecutive interiors, you may want to also have thought of this. You know that all the interior angles in a quadrilateral equal 360. They all measure up to equal 360. So we know this one's 23, that one's 23 right there, which is 46 if you add those together. And you could say these two are the ones you're looking for because they're going to be both the same because of the base angles theorem there too. So you could say those are both X. That would mean 2X plus 46 would equal 360. So that's another equation you could have used to get the same number here of 157 degrees. All right, number 3, so we have shown this is 130 degrees. We have a right angle here, which we know that to be 90 degrees. And then L and K, since this is a kite, showing us here, these are congruent on this side, these are congruent this side. So that is definitely a kite when you have congruent sides over here, congruent sides adjacent to each other here. And so we know that L and K are going to be congruent to each other. So they're the same thing. You can call both of them X right now if you want to. And then we can kind of put that together with our quadrilateral sum theorem. We could do the same thing and say, okay, this is 2x here, and you can add this up, 130 plus 90, and so that would give us 220 when you add the 130 and 90 together. Subtract 220 from 360, and so that now going to be 2x is equal to 140, divide by 2, and so x would be 70 degrees. So the measure of K and the measure of L are both going to be 70 degrees. All right, quick break for the joke of the day. How do astronomers organize a party? How do astronomers organize a party? They plan it. They plan it. Okay, back to trapezoids again. We're going to look at the mid-segment theorem for trapezoids. So a mid-segment is going right across the middle, connecting the two legs together of a trapezoid. So the mid-segment of a trapezoid is parallel to each base. So as you can see here, there's three parallels now. These are parallel, of course, but a mid-segment is going to be parallel to the bases. And its length is 1/2 the sum of the lengths of the bases. So if you add the bases together and you multiply it by half, that would be the length of the mid-segment. That's basically what it's showing you down here. MN, which is the mid-segment, is equal to 1/2 of AB plus CD. AB being the top base, CD at the bottom base. So if you add these two together and multiply by half, it will give you the length of MN. So just here's a couple problems out of the book that are like that. So it wants us to find the mid-segment here. It tells us the bases. So we just got to add these two together and divide by 2, basically. So 12 plus 28 gives us 40, and then half of 40 would be 20, and there it is. The MN would equal 20 inches in this case. Another one here where we're going to actually look at, going back to problem 1 on the extra practice. So this was looking like kind of problem 1 here. It wants us now to find the mid-segment here. What's the length of this mid-segment? So to do that, we would need to find the lengths of the bases. So our bases would have to be figured out. And it's not the slope we're looking for here, it's the distance formula that we have to use on this one. So we use the distance formula to find SV, and they plug it in there, subtracting x's and squaring it, plus subtracting y's and squaring it, all under one big square root. Gives them the square root of 20, which simplifies to 2 squared of 5. And then on this one, we do the same thing with TU, subtract the x's, square it, plus subtracting the y's and squaring it, give us square root of 80, which simplifies to 4 square root of 5. Remember, we're looking for perfect squares in here, and you can see on this one, the perfect square, and this one would be 4, and the square root of 4 is 2, but it still has a 5, because 4 times 5. This would be 16 times 5, and 16 would become that 4. So that's these ones. You have to add them together and then divide it by 2, or multiply by half. And that's what they're going to show you here. They have the half plus the sum of those two. Well, since they're under the same exact radical, they have like radicals. We can say 2 plus 4, giving us 6 square root of 5. Half of that would be 3 square root of 5. So that's our answer for YZ in terms of a radical. If we wanted to get a decimal form of that, we could, but it didn't ask for any decimal form here. It didn't say round the answer to the nearest tenth or hundredth, so we're just going to leave it in radical form. Okay, so going back to number 1 on the extra practice, we left off with this here, that it is a trapezoid, it's isosceles, but the last one here, then find the length of the mid-segment of the trapezoid. So we haven't done that yet, and that's what we need to still do on number 1 here. So we have to figure out the length of the bases. We figured out the lengths of these legs, telling us that it's isosceles, and that was easy, but this one, it's not going to be as easy to figure out the length of these bases here, because these are not either horizontal or vertical like these legs were. So we have to use the distance formula to be able to do that. So let's start with finding the the length of SR. So under one big square root, we're going to subtract the x's. So it's a negative 6 minus 0. So that's S and R. So that's these two. Negative 6 minus 0. And then 0 minus 6 for the y's. Squaring each of those. So when you do that, so you're going to get negative 6 squared plus another negative 6 squared, which is going to be both 36 plus 36. That's what we end up seeing here. So negative 6 squared plus negative 6 squared. And we simplify the parentheses. So now these will be both positive 36's. 6 times negative 6. So now we have 36 plus 36. And we add that together, and that will give us 72. So we have the square root of 72. And now let's look for any perfect squares in 72. And we know that 9 is in there. There's also a 4 in here too. 9 plus 4. We know 36 is also in there because we just added 36 together. So 36 times 2 is 72. That would be the best one probably to use. 36 times 2, and then 36 is 6. So the simplest form for that would be 6 square root of 2. Now for finding the TQ, so TQ would be using these points here. So negative 3 minus 0 for the x's, and then 0 minus negative 3, or 0 minus 3 for the y's. And so it's going to give us kind of a similar thing with negative 3 in negative 3's in both. So we're going to notice that it's got positive 9 plus 9. So this is going to be negative 3. So negative 3 times negative 3 is positive 9. Now the negative 3 times negative 3 is also positive 9. That adds together to give us 18. So the square root of 18, but again, since these are both 9s, and 9s are perfect square numbers, 9 times 2 is what we can see for this one, and then the square root of 9 is 3, so it's going to be 3 square root of 2. That helps us because these are like radicals now that we can just add the 6 and the 3 when we want to find the midsegment of this. So now to do the midsegment, it's going to be adding these two together and then multiplying by a half or dividing it by 2. So doing the midsegment, we are doing this. So 1/2 plus, or 1/2 times the length of these two added together. So 6 plus 3 gives us 9, so this will be 9 square root of 2. And then half of that, so we're going to see half of that's going to end up becoming 4.5 square root of 2. Now another way they might have this answer is if they didn't want any decimal to be here, they could have just said this divided by 2. So they could have said 9 square root of 2 over 2. That's another way they might have written the answer out as well. Let me just write that here just in case you want to see that. So it could have been like this as well. So 9 square root of 2 over 2. That's another way they could have written the answer out like that. That's the way they may have it on the big ideas perhaps. Okay, 4 and 5 are these are the easier ones where it's not on the coordinate plane, just shows us. And it says find CD, and CD in this one is the midsegment. So we're showing the two bases, 12 and 36. So we just quickly do that formula, 1/2 times the two bases added together. So we got to add 12 and 36 together. That would give us 48. So 1/2 of 48. Half of 48 would be 24. So that's the answer for this one. CD would be 24. This one, though, CD is one of the bases. It tells us the midsegment is 1.8 and the other base is 0.6. We're still going to use the same formula. We're just going to have to plug in kind of CD here is what we're looking for where it's a base. So it's a 1.8. That's going to be our midsegment is equal to half of this base plus the other base, but we don't know this base here. So first thing we're going to do is start to work this out. We can distribute if we want to on this one. So we can distribute the half into this. So now it's half of CD, and then half times 0.6 would just be 0.3. If you want to do that on a calculator, you can divide 0.6 by 2. It's 0.3. And then we can bring the 0.3 to the other side, so we get the 1/2 CD by itself. So subtract 0.3 from both sides, and now the 1/2 CD, that's going to equal 1.5. So kind of 1.8 minus 0.3 is 1.5. To get rid of your fraction here, multiply both sides by 2. So multiply both sides by 2. That will cancel the 2 and this half out, giving us just CD by itself, and then 2 times 1.5 is 3. So our answer for this one is 3 for up on top here. So this really should be the length of 3 for the other base. Okay, so here's just another property for a kite. So we already saw this property at the bottom, the 7.19, the opposite angles theorem. We already looked at that one. But there's a diagonal theorem for the kite as well. And that's where the diagonals in a kite are perpendicular to each other. They're not congruent. They're perpendicular to each other. So it says if quadrilateral ABC is a kite, then AC is perpendicular to BD. And another thing that I might just put in here for you is that it actually this diagonal right here actually bisects this one. So here's another thing you can actually know is that these are going to now be congruent to each other. This BD segment here, this diagonal will bisect the AC diagonal. So that means that these will actually be congruent. So you can mark that there on your paper, that these here will be congruent to each other. So if you know this side, it's the same on this side. Okay, last couple problems here for the lesson, almost done. Find the value of x on number 6 and 7. So if we want to figure out what the value of x is, it tells us the bases here are these expressions. Your mid-segment is this expression. So how would we do this? How would we figure this out? Well, we could put it into the formula for the mid-segment theorem of the trapezoid, which would be this one again. So you can say mid-segment is equal to 1/2 times the two bases added together. So you can put everything in. So our mid-segment would be the 3x minus 2 over here, and inside here would be our two bases that we can add together. So that would give us an equation that we can put it all together and then solve. So here I want to do what's inside the parentheses and want to combine like terms inside here and then probably distribute the 1/2. So first of all, we'll do that. So x plus 3x would give us a 4x inside. 11 plus 3 is 14. And then I can distribute the 1/2 into that, basically half of each of these. So that's going to give us a 2x and then a 7. So our 3x minus 2 over here, that's the mid-segment. That's just hanging out here for a minute. So now I have 2x plus 7 on this side, and then I just want to solve for x. Let's get the x's together. So I probably want to subtract 2x, get them all together on the left side over here. So subtract 2x from both sides. So that would give us now 1x minus 2 is equal to 7. These will cancel out here. So 1x minus 2 is equal to 7, and then you can just add 2 to both sides, and that would mean x is equal to 9. So there's our answer for x. Finding the value of x, x would be 9. Number 7, we have a kite. As you can see, the kite is clearly here marked, so you have your two congruent sides up on top, and the two on the bottom are congruent. Shows us diagonals in this kite. It tells it that the diagonal here is 9 on this side and 1/10 x minus 1. So here's where that theorem that I was telling you about, that little extra piece that I gave you for free, this is congruent to this side. So these are congruent to each other. 9 is equal to the 1/10 x minus 1. So we can make an equation out of that by setting those equal to each other. 1/10 x minus 1 is equal to 9 because the GF diagonal is going to bisect the HF. GE is bisecting HF here. So what I first do would probably be to add 1 to both sides and get the x term by itself. So that's going to give us 10 on this side. So 1/10 x is equal to 10. And then to get rid of the fraction, we want to multiply both sides by 10. And so when we do that, that gets rid of the fraction here. It leaves us just with x, and x is 10 times 10, which would be 100. So your x for this one on number 7 is 100. All right, that finishes our lessons for Chapter 7. Now you just need to finish up all your homework, and you'll be done with all the assignments and everything for 7. All right, I'll see you there in class.